Limits and continuity. So the first three graphs that we have are examples of graphs that are continuous at an x value of c. And again, we're only looking at the x value of c. So if I look at this x value of c right here, I know this is continuous because from the left and the right side, I don't have to lift up my pencil to go through that point. Same thing for the next graph. From the left and the right side, I don't have to lift up my pencil to get to the point C, and same thing on this last graph here. So now, again, we're only looking at this x value of c on our graph because we know these last two graphs, the entire graph is discontinuous because we can see that there's a break in the graph right here, and here we can see that there's a jump in the graph. But again, we're only looking at the x value of c for each of the graphs, and at that x value, we know that it's continuous. So these next four graphs are examples of graphs that are discontinuous at x equals c. So if we look at this first one, this is a removable point discontinuity because you can see from here to get to C, I'd have to lift up my pencil and then come back down to trace my graph at the x value of C. Therefore, it's not continuous. Looking at this one right here, this is an infinite discontinuity because we can see those parts going up to infinity. Then we have a jump or a break in our graph, I should say, to get to this side. Over here, we have a jump because at C, I'm coming up here as well. And then down here, we just have a hole. So at C, I'd have to lift my pencil up to get to the other side. So again, those are all discontinuous at x equals c. So remember before we talked about being able to tell whether or not something's continuous by taking your pencil, and if you can draw your graph or retrace your graph from left to right without picking it up, we said that that meant it was a continuous graph. Well, that doesn't really help us when we're getting up into upper level math and calculus. We actually need to have some kind of definition in order to help us. So this is actually the definition of continuity, and we use this definition in these three specific rules we have to define when we're trying to say whether or not something is or is not continuous. So for the first part of the rule, you have to say f is defined at c, so that means that c is in the domain of f, so that f of c equals some number. So number two, you have to show that the limit as x approaches c of f of x exists. And the third part of the rule is the two have to be equal to each other. If f is not continuous at c, of course we say it's discontinuous at that value of c then. So if we go ahead and we're going to use the definition of continuity and this graph of f of x below to explain why the function is discontinuous at these three values that we have for x. So the first part, we're going to look at x is equal to 3. So for an x value of 3, if I go to my graph here, I can see the first part of my definition says we want to figure out what f of 3 is equal to. If I look at my graph, I can see I have a hole right there, and there is no other dot on my graph, so therefore f of 3 is undefined. Now I know that since it fails that first rule that it's going to be discontinuous, but we're going to go ahead and finish the rest of the definition. So the second part of the definition is the limit as x approaches 3 for this function f of x is equal to, so from the left side and the right side, the limit is approaching this y value of 10. And the third part of the rule is to state that f of 3 in this case does not equal the limit as x approaches 3 for this function. Therefore, or in conclusion, that's what these three dots mean. So thus, the graph is discontinuous at x equals 3. And again, so we just showed using the definition why we are discontinuous at this point. So again, it's not good enough to say anymore that because as I moved across my graph, I had to lift up my pencil to get to the other side. So now we need to use this actual definition. So then let's look at an x value of 7. So same thing. So here is 7 on my graph. So the first thing I want to do is look at f of 7. Because it has a closed circle right here, we know that f of 7 is defined at a y value of 12. So then the second part is looking at the limits as x approaches 7 for this function f of x. So from the left side of our function, we are approaching a y value of 12. From the right side, we're approaching 5, 6, 7, looks like 8. So because the left and the right side are coming to two different values, I know that the limit as x approaches 7 for this function does not exist, so D and E. And the third part would be to state that f of 7 therefore does not equal the limit as x approaches 7 for the function f of x. Thus, or therefore in conclusion, it's discontinuous at an x value of 7. So now let's go ahead and look at an x value of 10. So for x equals 10, we're going to do the same thing. So the first part of my rule is to define what f of 10 is equal to. So at 10, we see a closed circle right here, so it's equal to 9. Then the second part of the rule is looking at the limit as x approaches 10 for the function f of x. So as we are approaching an x value of 10, from the left side and the right side, we're approaching the same value, which is 11. And the third part of the rule, f of 10, now you can see, does not equal the limit as x approaches 10 for the function. So therefore, it's discontinuous at an x value equal to 10. And so again, the first one failed the rule at number 1, the second one failed the rule at number 2, and this third one failed the rule at number 3. So these are 3 different examples of where our rule can fail to have something exist, therefore it is discontinuous at that point. So let's actually start to maybe think about a value that may work on this graph. So let's go ahead and give an example of that just so you all can see. So let's go ahead and I'm just going to pick an x value of, let's just do 1 because that's easy, it's right there. So if I wanted to show for x equals 1 that the graph is continuous at that value, I would again do my 3 parts of my rule. So the first part of my rule would be that f of 1 is equal to, and you can see it's equal to 8. And the second part would be the limit as x is approaching 1 for f of x. Oops. Is equal to, and you can also see from the left and the right side, we're also approaching 8. And the third part would be, since f of 1 equals the limit as x approaches 1 for the function f of x, therefore, or in conclusion, the graph is continuous at an x value equal to 1. So for the next example, it says determine all the numbers for which the function is continuous using the definition of continuity. So a lot of the times it's easier to prove something is continuous by proving where it maybe not be continuous. So remember, things are not continuous when we have our vertical asymptotes or the holes on our graph. So that's what we're going to take a look at for these two functions. So we have a piecewise defined function here. And the first thing I'm going to do is go ahead and look at this top part right here of my function, and I'm going to factor that. So that factors into x plus 2 times x minus 1 over x minus 3 times x minus 1. And so then you can see right here that the x minus 1's cancel out, so that means we have a hole in our graph at an x value of 1. So then for this we get x plus 2 over x minus 3. So we know for the top function there's a hole at an x value equal to 1. And we also have a vertical asymptote at x is equal to 3. So the domain of this function, of course, is going to be all real numbers except for 1 and 3. And if we look at the next part of our function, so for this next one right here, this is saying we have y is equal to negative 3 halves, which is a horizontal line. However, because of the rule right here, we're saying it's only for the x value equal to 1. So that means we only have the point 1 comma negative 3 halves on our graph. So it'd actually just be a point on the graph. Whereas this one said for x values not equal to 1, so we don't have to worry about this hole. So let's go ahead and use our definition to prove or disprove whether or not it's continuous or discontinuous at those certain values. So for this one, let's go ahead and look at an x value of 1 first. So for an x value equal to 1, the first thing we want to look at is f of 1 defined for this function that we have right here? So if I plug 1 in for x here, then I know that because it's x equals 1 right here, I'm using this bottom function. So I would get negative 3 halves. So then for the second part, I have to look at the limit as x is approaching 1 for the function. And so remember, that means you're looking at the left and the right side of 1 and what's happening, what it's approaching. So if I'm looking at the left and the right side of 1, I would actually be using this top equation right here on my graph. And remember, when we're trying to figure out where the hole is, we can use our simplified answer here. So if I take this and I plug in a value of 1, I would get 1 plus 2 over 1 minus 3, which is equal to 3 over negative 2, so negative 3 halves. So that's where the hole would be located, at 1 negative 3 halves. So that means if we were to graph this function, we know that there's just a hole on that part of my function. So the left and the right side of my graph is going to be coming to negative 3 halves. And so now you can see then for number 3, since f of 1 is equal to the limit as x approaches 1 for this function, because they both equal negative 3 halves, therefore, or in conclusion, we know our graph is continuous at x equals 1. So then the next part that we need to look at, because we had two places we were concerned about for our domain, we have to look at an x value of 3 where we have that vertical asymptote. So now I'm going to go ahead and do the same thing, except for look at an x value of 3. So for an x value of 3, we want to do the same thing. So first I want to look at f of 3 and what it is equal to. So if I'm looking at f of 3, we know that for f of 3, we would actually be using this top equation, and the reason we're using the top equation is because this is only for x values not equal to 1, and this is for only the x values equal to 1. So if I plug 3 into the original equation, or even the simplified one, you can still see that it makes your denominator 0 because there's a vertical asymptote there. Therefore, we know it's undefined here because of that vertical asymptote. And if I do the second part of the rule, the limit as x approaches 3 for f of x. So if I were to think about the graph of this, I would have to figure out what's the left and the right side doing for my graph. Well, because we have an asymptote there, it's either going to go to infinity or negative infinity, so therefore it does not exist. And so the third part of the rule, since f of 3 does not equal the limit as x approaches 3 for this function of x, thus the graph is discontinuous at an x value equal to 3. So that tells us then that the graph for this piecewise defined function is going to be continuous at every x value except for an x value equal to 3. So the last part would be to write out your final answer. So my concluding statement would be f of x is continuous for all real numbers except for when x is equal to 3 by the definition of continuity. And again, the reason we were able to figure that out was because it asked us to figure out for all the numbers which the function is continuous. So we wanted to look at where our graph is not defined. And again, we learned a lot about how to find the domain of a function by looking at, and also finding the holes and vertical asymptotes. So looking at the denominator, setting equal to 0, not equal to 0, and figuring out those values. So for these next two, it says use the definition of continuity and the properties of limits to show that the function is continuous at the given number. So if we look at this first one, we'll do this one together. Right away, I would notice that this is a polynomial function if I were to FOIL this out and combine like terms. So I already know that the domain of this function is going to be all real numbers, so there's no values in the denominator that I have to watch out for. And we're looking at an x value of 1. So for this, if I want to show this continuous at this number, which I already know it's going to be because the domain's all real numbers, I can go ahead and use my definition. So for the first part, f of -1, we have to plug -1 into g of x, and I guess I should use g of -1, not f, since we're using g of x. So g of -1 would be equal to -1 squared minus 3 times -1 minus 10. And then we do it again, so -1 squared minus 3 times -1 minus 10. And so when you evaluate that, you get g of -1 is equal to, in this case, 36. So the next part would be to look at the limit. So the limit as x approaches -1 for g of x is also going to be equal to 36. And we know that, again, because the domain of this function, since it's a polynomial, is going to be all real numbers. We don't have any variables in the denominator, and we don't have any variables underneath an even root. So that's how I know it's going to be equal. And you can also confirm that by looking at the graph on your graphing calculator. So for the third part, now I've just proved that g of -1 is equal to the limit as x approaches -1 for this function, because they both equal 36. Therefore, or in conclusion, the graph is continuous at an x value equal to -1. So I want you guys to do this problem on your own and bring it to class.